Swayam Prabha. Digital India. Educated India.
Welcome to this lecture on transition metal organometallic chemistry from principles to applications. We have been looking at a very important class of compounds, particularly the transition metal carbonyl compounds in the last few lectures. These compounds, as mentioned, that these are very long known in the field of organometallic compounds, unlike the carbene-carbine complexes which were discovered recently. Transition metal carbonyl have been known for more than a century in the area of transition metal organometallic complexes. However, what is interesting about these transition metal carbonyl compounds is the fact that even though they have been long discovered for over a century, their bonding properties have only been recently studied and understood. So, these transition metal carbonyl compounds, even though they have been discovered for over a century, their bonding properties are only being recently understood. So, in the last lecture what we have discussed was the type of bonding modes of these transition metal carbonyl complexes. And what we had seen that transition metal carbonyls can be the terminal ones of the ones which is shown. This is the terminal carbonyl. It can also be a bridging type. Or can be semi bridging, as one can see from here. Of the type this, and a very nice example of the semi bridging complex was achieved by binding to a bipyridine ligand in a iron carbonyl compound. Where it was found that the semi bridging interaction occurs when this bipyridine ligand, which makes the iron more electron rich, interact with the pi star orbital of this carbon monoxide ligand, and leading to this semi bridging bonding that we had seen. And this semi bridging arises because of disproportionate electron density between the two iron centers, and that arises because of replacement of carbonyl by the strongly electron sigma donor bipyridine ligand. Now, continuing further on this discussion, we are going to look at various kinds of unsymmetrical sigma pi bridging in metal carbonyls, and this is given by metal carbonyls, and one can see that apart from the semi bridging which we had just discussed, there can be unsymmetrical sigma pi kind of bridging which is shown over here. So, here it is pi type interaction from the carbonyl, and here it is sigma type. On the other hand, the semi bridging ones that we had just now seen, that was slightly different from this, in the sense that this metal was interacting with the CO carbon, whereas the second metal is interacting with the CO pi cloud. So, this is pi type and this is sigma type, and this is how this kind of bonding is different from semi bridging. And this is sigma pi type pi nuclear bridging. There are other variants of this sigma pi bridging, which can extend from one metal center to another metal center, as can be seen over here. Now, in this case, this is pi, this is sigma, and this is sigma. This is also bridging. Now, bridging over 3 metal centers. There is a variation of this, where this is sigma sigma pi, one can have slightly different So, in this case, this is sigma pi pi bridging, and another very interesting example involved this is sigma 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 pi type. So, bridging. Now, as one can see that carbon monoxide can act as 4 or 6 electron donors, and shows side-on coordination. Now, in order to understand how does this carbon monoxide unit interacts with the metal frontier orbital, one needs to look at what is the bonding scenario of CO or carbon monoxide. Before that, we are going to take a look at some of the examples of sigma pi bridging carbonyls which have been structurally characterized. One such example is this manganese complex, which is this Mn2CO5 moiety in mu pH2 P CH2 P pH2 whole 2 Mn2CO5. For clarity purpose, this mu pH2 C pH2 moiety is omitted for sake of clarity of the drawing, and this sigma pi bridging example of manganese can be seen over here. For example, it is Mn, CO, 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 CO. Now, manganese distance is 293 picometer, manganese carbon distance is 166 picometer, terminal carbonyl, and CO distance is 121 picometer. In this terminal carbonyl, this distance it was 166, this is 175 picometer, and this carbon monoxide is 116 picometer. Now, this is a bridging carbonyl. So, this has a greater manganese carbon distance of 193 picometer, and this the pi interaction is 201 picometer and 229 picometer, and this CO is 110 picometer. Similarly, another example is this bridging sigma pi bridging carbonyl is found in Nb3 mu CO unit. Moiety in Cp Nb CO 2 whole 3 mu CO. Here too we see similar sigma pi bridging happening. So, we have Nb, three of them, then CO, this CO is bounded to, this is sigma pi pi. So, this CO is bounded to one Nb, another, then same CO is bounded to another niobium, and this NBC bridging distance is 197 picometer, the CO is 130 picometer, and NBO is 224 picometer, and NBO is 221 picometer. So, what we see by comparing these two structures, that these sigma pi bridging compounds are present in big cluster compounds with having bulky ligands, and what also we see that the bridging carbonyl metal carbonyl distances are around 200 picometer, 193 picometer for manganese and 197 for picometer for niobium, and also the CO metal interaction on the side one overlap is around 221 to 229 picometer, and same we can see in case of the niobium. So, what we see is that these bridging sigma pi carbonyl compounds exhibit longer metal carbon distance as is expected, and also the pi interaction with the metal is even weaker, and that even gives even longer distances. So, these two are pi bridging. So, pi electron interaction with the metal, and they are the longest, and this is a sigma interaction with the metal, and so hence this has a shorter bond, and same thing we see for the manganese complex as well as for the niobium complex. In both of these complexes, this bulky ligand mu PH2P CH2PH, or in the niobium case Cp niobium CO2, those bulky ligands has been Cp and CO2 have been omitted for sake of clarity. Okay. So, with this as I said that to understand the sigma pi bridging nature, one has to look at the molecular orbital diagram of the carbonyl to get a clear picture of how the carbonyl frontier orbitals interacts with these metal frontier orbital. So, to understand this, let us sort of take a look at the frontier molecular orbital of CO. So, we have carbon monoxide, we have oxygen. Carbon has S and P as the valence electron. So, this is the S orbital, and then this is the p orbital, 2s to p, and oxygen is also has s and p orbital, but oxygen being more electronegative, this orbital are more closely held to the oxygen. So, this becomes s, and these become p orbitals for oxygen. Carbon has P2 configuration. So, there are 2 on the P and the S is full. Oxygen has P6. So, there are 4 in the P and 2 on the oxygen, and the S of carbon interact with the S of oxygen and to give sigma bonding interaction as well as a sigma star interaction. So, this is sigma or S sigma 3 sigma, and this is S sigma star, this is 5 sigma orbital. Okay. Now, as far as the p orbitals are concerned, there is one s and 2 p interactions. So, first is the pz interacting with pz. So, giving p sigma orbital. This is p sigma or 4 sigma orbital, and that gives a p sigma star or 6 sigma orbital. So, that interacts with one of the p orbital of oxygen, giving p orbital of carbon, giving the corresponding sigma star, and that leaves with 2 p y orbitals, which are p pi type, and these are degenerate. And then these are p pi star 2 pi type. Okay. Now, with these there are 10 electrons, 4 plus 6. So, 2, 4, 8 and 10, all of these are occupied. So, what is important over here is this frontier orbitals. Frontier orbital is 5 sigma star is the frontier orbital. Now, 5 sigma star sort of looks like something like this. something. So, you have this something like this, and this is the frontier orbital, and then this pi star is the empty CO orbital. So, the pi star would look like this is p pi star. So, one orbital would look something like this. This is degenerate. So, it has 2 orbitals. So, the other so, this is also a pi star orbital, and similarly the sigma orbital would look like this is p sigma orbital, and the corresponding the p pi orbital would look like and so, this is the corresponding pi orbital. Now, if we look at it, so this gives us a fair about of idea about how these CO orbitals looks like. What we see is that the carbon CO interaction consists of s and p orbitals of the carbon interacting with s and p orbitals of the oxygen. The oxygen or molecular orbitals are low line in energy, and as a result there are 3 sigma bonds. This is the sigma between the s, this is the sigma between the pi orbital, which is shown over here, and this is the pi star orbital, sigma between pi. This is the py orbitals bonding, 2 of them degenerate in perpendicular plane of each other. Now, this is the sigma star orbital, which is over here, and then the pi star orbital comes around over here. Now, these are the 5 sigma star and p pi star are the frontier molecular orbitals, and these frontier molecular orbitals interact with the metal orbitals, and then corresponding the binding modes of how these frontier molecular orbital interacts with the metal come into picture. So, the thing that we should focus now on is these 4 orbitals. So, this is the HOMO and these are the LUMOs, where these are pi star orbitals and the HOMO is the sigma star orbital, which interact with the metal when it comes to the metal carbonyl interaction. So, with this let me conclude what we have discussed in today's lecture. Today's lecture covers a very important topic which is very fundamental and needs to be elaborated with proper understanding, and what we have discussed today is about the binding modes of metal carbonyl. Particularly in this lecture we have started with semi bridging modes of metal carbonyl complexes, in which a metal bridges with the carbonyl complexes. Then we have looked at various possible examples that may arise out of sigma and pi bridging type of carbonyl complexes. These are different from the semi bridging ones, and we have elaborated that with examples. We have seen in sigma pi bridging kind of complexes, carbon monoxide CO can donate as many as up to 4 or 6 pi electrons, and these may lead to sidewise overlap, which is a new kind of binding mode of carbon monoxide. We have looked into specific examples where like Mn2CO5 in a particular complex, where you can see this sigma pi bridging type of carbon monoxides. These examples have been structurally characterized, and then we have looked into the metal carbonyl interactions, particularly with respect to this bridging sigma and pi type, and for that reason we have constructed this MO molecular orbital correlation diagram between the CO unit, between the S and the P orbitals of the carbon monoxide, and we have seen how these orbitals are formed by mutual interaction, and we have identified this 5 sigma as a the HOMO, which is a lone pair on the carbon monoxide. The orbital is very close to the carbon in energy, that is why this HOMO represents more on carbon, which binds to the metal. And then we also have identified degenerate p type, pi type, pi star type orbitals, which are empty and they can accept electrons when they interact with the metals. We have looked at the corresponding molecular orbital diagrams of these orbitals constructed from atomic orbitals of these carbon and oxygen fragments. So, with these I would like to conclude today's discussions on this bridging mode of carbon monoxide, and we are going to take this discussion a bit more detail in the subsequent lecture, whereby we will see that how this CO molecular orbital constructed in this lecture help us understand and realize the subsequent interaction of this metal carbonyl with metal fragment molecular orbitals. So, these will throw some insight as to how carbon monoxide binds and bridges with the metal in a terminal or a bridging fashion. So, with this I would like to conclude today's lecture and thank you for being with me till the next lecture, which will be on more of binding modes of carbon monoxide and their understanding at a molecular orbital level. So, till then goodbye and thank you.